good evening, everybody. Thanks for showing up this evening to listen to an exciting lecture on machine learning for connected cars. My name is Pradeep Kumar. I'm the Oregon Chair for the Communication Society. And with me as moderator is Raf Ganatambi. He will be, he's a vice chair and will be moderating the event today. And without further ado, I am going to hand over to Raf, who will introduce the speaker. Thank you.
Right. Thank you, Pradeep. I'm very happy to introduce my friend Dr. Alvin Chen, who is with the BMW Technology Corporation, located California Bay Area, where he researches on AI and emerging technologies. Previously, he was a senior machine learning researcher at the BMW Technology Corporation in Chicago, where he worked in big data and machine learning for improving driving behavior. Prior to BMW, he was a senior researcher at Microsoft in Beijing, working on big data analytics, and he was a senior researcher at Nokia Research Center working on mobile social networking. Dr. Chen has authored more than 30 papers and 15 patents. Alvin has a BS degree and a MS degree in computer engineering from the University of Waterloo and a PhD in computer science from the University of Toronto. He is the chair of IEEE VTS Chicago, and Alvin is a senior member of both ACM and IEEE. So for this talk today, Alvin is okay with having some interruption during the talk for a few clarification questions, but most of the bulk of the question we can keep it at the end of the presentation, after the presentation. So folks, on Zoom, if you have any clarifying questions, you can interrupt and ask your question. If the interruption become too much, we may push the questions to the end. With no further ado, let's welcome Dr. Alvin Chen.
All right, thank you, Pradeep, and thank you, Raf. So it's interesting because actually I know Raf because the last time we actually met together, right? I think it was physically 2 years ago, right? At Vehicle Technology Conference 2019.
Yes, VTC and then Globecom 2019 Globecom as well, right? Yeah.
No, actually, Globecom I wasn't there. Actually, Globecom.
So okay, VTC only, right.
So it was VTC, and it was in Hawaii, which I wish I was there right now. But anyway, yes. So thank you very much to Pradeep and Raf, and I'm really glad to be here this evening to talk to you guys regarding about machine learning for the connected car. So this is work that I've been doing that I will show tonight was work that I did when I was previously working in the BMW tech office in Chicago before moving over to the Silicon Valley tech office. So all this here is regarding about my previous work here. Okay, so. All right, so everybody knows, right, for, automated vehicles, autonomous vehicles, that, a lot of the stuff that's being done in autonomous vehicles, machine learning is being done in order to identify, particular objects or so in the windshield and being able to have the vehicles to steer properly. But I think what a lot of people don't really realize too, as well, is that we also have machine learning for connected vehicles, right? Vehicles that are connected to each other and connected to 5G and connected to the infrastructure. So I'm actually going to explain to you why we do need to have machine learning for connected vehicles. And I'll start by having this kind of slide here. That basically what connected vehicles does is that it brings digitalization into the vehicle. Okay, so because now you have access, and you have the data, and you have connection to the internet now, then what happens now is that the data that comes from the car is now being uploaded to the cloud. And then from the cloud, you can do big data and predictive analytics quite easily and be able to use machine learning to get intelligence. And then once you have that intelligence, you can be able to tie it down to the car, or you can put it to like an app. And I'll actually will explain how in Chicago we created an app to do that. Also as well, people bring into the car, their personal smart devices, right? Their phones and watches. And how do you synchronize, all that information that you have? Let's say, different stuff on your calendar, how can they show up as trips or so in the car? And then finally, of course, the Internet of Things, right? So IoT. And so how do we go ahead and integrate the connected vehicle with your IoT devices? Like, for example, you can tell, let's say, Amazon Echo and say, hey, BMW, when is my next trip? And actually, we did do that type of functionality. Okay, so then why do we need machine learning in the vehicle for connected vehicles? So first of all, some of this is already pretty obvious, right? So we have that so we can be able to improve, traffic and road safety. Obviously, like I said earlier, for autonomous driving and for integrating with the smart city, right? So with the smart city, we have a lot of, now sensors that are in traffic lights, sensors and a lot of different types of infrastructure. And so if you can be able to integrate it with the smart city, then the vehicle can be able to do particular actions that are based upon the real-time data that's happening. But one of the things that maybe you may not have thought about, and this is where we actually, I did some work in while in the Chicago tech office, is journey management, right? So you can think about, how machine learning can be done to help you to prepare to manage your journeys. Also, as well, for predictive vehicle maintenance, how many times or so you take your vehicle into the dealership because something happened or so. AI could be used to be able to determine something was at fault or something is about to fail before it actually fails. So that's predictive vehicle maintenance. And the third one is about personal preferences, so personalization. And I'll give an example use case or so for each of these. So first of all, I am going to talk about machine learning for journey management. So the whole idea here is that at BMW, when we first of all, created our BMW connected product, which was about, I would say now about almost 5 years ago or so, we thought about, the customer, right? The BMW buys the vehicle, has a luxury vehicle, and they want to basically, how do they able to integrate or use all the services and data that they have, on their smartphone to be able to connect it to the car, right? So how do we create this kind of like seamless user experience? So how do we improve the user and car experience to meet customers' individual mobility needs? So if you think about it throughout the day or throughout the week, what happens to the customer, right? The customer goes into the car, leaves from home, let's say goes to work, but also needs to be able to find a parking spot. She also has some personalization, so maybe wants to listen to a particular type of music. You need to find, where the gas station is, which one, maybe what happens is that, the gas is low, but you have some specific preference as to what gas, preference in terms of what maybe brand that you like. And then, so how can they go ahead and recommend to you, the appropriate, gas station to get there? Or as well, in terms of the weather and the traffic. So you can see here, the whole idea here is to kind of take all the things that a customer does in the daily life and be able to kind of put that into the car. So to kind of like have that kind of integration there. Okay, so like I said earlier, this is where we actually launched a product in the Chicago office that was called BMW Connected. And basically that's what it did. Basically what it did is that it's recorded data from your vehicle. So recorded location data, temperature data, other types of data from the sensors in the car, and was able to tell you, for example, when would be your next trip. It would tell you, recommend, for example, the nearest, gas station that you needed to go to fill up gas, or even as well to even precondition your car. So for example, it would tell you in advance if you needed to, let's say, heat up the car in advance based upon your previous, what you've done in the past. Okay, so that's BMW connected, and now that actually is being replaced with a new app which is called My BMW app. And basically, what it's trying to do is connect your vehicle to your life. Okay, so what we did in BMW Connected. So I worked in the machine learning team in BMW Connected in Chicago, and our team was actually tasked with trying to create machine learning algorithms for understanding driver behavior related to journey management. So if you think about it, when a user is driving the car, what's the first thing that needs to happen? Well, first of all, you need to learn where the user went, right? So we have to learn what's called a destination. So how do we learn a destination here? So the thing is that when you're driving, you're collecting all this location data that BMW Connected is doing, and then when you arrive at the destination, then you have a whole bunch of particular points. So you can see here, I have a whole bunch of location points that I parked the car. And then what happens is that it's using a machine learning algorithm, which is basically clustering, right? So it's trying to determine where you actually park the car. Okay, so we do clustering here, and then from this clustering, we find the center of the cluster. From the center of the cluster, then we know what the latitude and longitude is. We can do reverse geocoding to find the address. And then from there, so you see here, this address actually corresponds to 14 West Superior Street in Chicago. And then if we take that, address and put it into some type of, point of interest labeling. So in this case here, we use the Here Maps API to do this. Then we can refer to that this 14 West Superior Street actually means Holy Name Cathedral. So this is the interface in BMW Connected based upon the places that I've gone, and it shows up here in the screen. Okay, so basically in a nutshell, what we did here is that we processed the trip data to be completed, and we have to identify stay points, because one of the problems is that what happens if a particular person is driving and it just stops for like maybe a couple of seconds or maybe a couple of minutes and then continues onward, right? So we don't want to identify the false particular destinations. So we kind of define a destination as to you stayed there for a certain amount of time. So for example, you stay there for at least 10 minutes. So we call that the stay point. Okay, so we identify stay points for each trip. And then we use spatial data clustering. In terms of the actual clustering we did a form of hierarchical clustering. And then from there, then we can determine, for example, we would know where your home is and where your work is, depending on the particular rules and temporal behavior. So that's for learned destinations. Okay, so once we know the learned destinations, then come the trips. Okay, so let's say you're going from home to work, right? And home is a frequent destination because you go there all the time as well as for work. Then because you are driving from home to work, let's say every day at a certain period of time, then that becomes a frequent trip. Once that becomes a frequent trip, then we kind of can be able to go ahead and model the trip departure as well as the trip arrival. And once we can model that, then that is called a predicted trip. So we'll know that, let's say after a week, once we learn your behavior, then we'll know for sure that, the next Monday you go to, you should be leaving at some particular time in order to go to work. So basically, kind of in detail, what we're doing here is that, we first go do trip data processing, right? So we're identifying the trip segments, the stay points. We do the clustering, which I mentioned on the previous slide. And then we determine based on that, whether the person's at home, work, or maybe at school. And then we do predictive modeling. So we look at the destination arrival behavior, the stay duration modeling. We learn the departure behavior. And then from there, we combine together to get a predictive departure time. So we know that, for example, that let's say you depart at around maybe 8 a.m. To leave home in order to go to work. Okay, so we use something that's called contextual association rule mining. And basically what this is trying to do here is that it's trying to find the frequent co-occurring associations among a collection of items in certain contexts. So for example, what contextual association rule mining could do is that based upon your trips, it would then determine and say that, okay, the context, right? So if the time is Monday, and if the range is between 6:30 and 7, then you drove from home to the railway station because you went there to take the train to get into work. Okay, so this is the predicted trip. We created a predicted trip algorithm based upon this, and then we would then tell users, when would be their next trip. And then next slide here shows you how from the algorithm we display it to the user. So you can see here on the left, you can see we got notifications that says, leave in 10 minutes to get to driverless city, right? So this is something that we predicted that I'm going to this next trip. And then you can see here, these are the list of all the particular trips. And then, for example, if I need to go to here, then it's very simple because I could just go ahead and click on go, and then it would go ahead and send that directly to my vehicle. And then I can go to my next trip. And then as well, in BMW Connected, we could also do scheduled meetings. So what happened as well is that, you have meetings in your Outlook calendar, and those Outlook stuff, or Gmail or Google, and it gets synced to your phone. Okay, and so BMW Connected takes all the calendar meetings that you have on the phone and then sends it to the BMW Connected cloud, and then from there creates a trip based on that. So here's one example trip that I had. Actually, this is the talk that I gave at the BMW Tech Office in Chicago, 540 West Madison, and you can see I gave another machine learning talk to as well to the office. And then so you can see here that I have the BMW Connected interface. So this is the calendar entry. And this calendar entry gets converted into a trip here that's in BMW Connected. And then when I hit go, it will go directly to the vehicle. So if I'm in the vehicle, this will automatically connect to the head unit and be able to send it there. If I hit send to vehicle, that means that if I'm not in the vehicle, so let's say I'm at home or I'm wherever, I can just send it to the internet. And then when I get into the car, it will pop up when I start driving. And then you can see here that I have a notification that says leave in 15 minutes to get to this meeting. And then it will automatically pop up. So here you can see I have this screenshot where actually I was in an i3, and then in the i3 it popped up with this message. And then I can just easily go ahead and use the BMW, the iDrive, the knob to be able to select it and be able to go. Okay, so that kind of gives you an example in terms of how we had the machine learning algorithm for learning destinations, for learning particular trips, and then how that actually is sent and delivered to the user. Okay, so that's on predicted trips. Another thing as well that we did as well is that we learned fuel consumption after a trip. So one of the things that we found out is that when you're driving, the gauge shows you, how much fuel that you've consumed, right, in terms of miles per gallon or in terms of number of gallons you have remaining. But a lot of times, this particular number is not very, very accurate because it's depending on, how fast you're driving in terms of other environmental factors. If you were, let's say, sloped on a hill or going downhill, okay, so it's not always very accurate. So what we wanted to do here is that we wanted to actually use a machine learning algorithm to be able to actually more accurately tell you in terms of your fuel consumption. So one of the features that we created in BMW Connected was called a trip summary. So what happened here is that if you're driving, let's say in this case here, I was driving from Schaumburg, which is a suburb in Chicago, to downtown Chicago, then during that particular trip, it would tell me the summary of what happened during that trip. So if I click on here where it says more details, I come to this screen here that tells me all the details of that trip. So it tells me that what time I left, what time I arrived, shows me on the map. It also tells me what is the trip time, the distance, the average speed, and the fuel used. Okay, and then how is the fuel used is calculated is based upon this particular algorithm. So what we did here was that we first of all grabbed the data in terms of the average travel speed, and also in terms of the fuel consumption rate, and then from here we kind of fitted a function that goes to these particular points. And in this case here, we used a Gaussian function. And you can see on the right here, that was kind of the equation that we used. So we have the speed here, the travel speed in TS there. And then basically we just use this equation in production to be able to then say, depending on your speed, we do the calculation, we get the kilometers per liter, then we can know what distance you traveled. And then from there, we can get the actual fuel consumption in terms of liters in this case. Okay, so that is hopefully that's a kind of gives you the first use case in terms of for journey management, how machine learning can be there, can be used for that. So the next topic I'm going to talk about is on predictive vehicle maintenance. So this particular work was actually a paper that I actually wrote together with my manager at the time and also a PhD intern who came to us from Munich. And this work is about using creating a data-driven automotive diagnostics using the cloud IoT edge framework. And this work was actually presented at a Vehicle Technology Conference 2019 fall when we were actually physically could go in Honolulu. Okay, so what's the background behind this, right? So basically what we're trying to do here is that we want to detect early faults before they become failures, right? So for a customer, a customer does not want to wait that, oh, the car all of a sudden some particular part fails and then have to go directly to the dealership, right? It's inconvenience. So there's a way that we can be able to predict earlier in advance that some particular component is a fault before actually becoming a failure, then that would work help tremendously. So in this particular area or so, there you can be able to detect early faults, and some approaches do rule-based and model-based. But because now vehicles they're so complex and they have so much rich data, they don't work very well. Now, the thing is that, you can use machine learning and deep learning to be able to perform this data-driven automotive diagnostics, but they are done, off-board, and so they're not, automated. So the example use case that I'm going to be explaining is that of detecting pre-ignitions before they cause serious material damage to the engine of the car. And that's actually the data set that we use in order to detect whether we have a pre-ignition or not. So if you don't know what a pre-ignition is, basically what it is that it's, so when you start the car, right, there's a spark, right, to the engine that goes ahead and then you have the car running. In this case here, what a pre-ignition means is that this happens even before, right, before you actually even start the car, which can happen. So basically it's a kind of a chemical reaction, right? So it's a combustion of the fuel-air mixture in a cylinder, which is not triggered by a spark, but by a hot spot prior to the spark timing. So I'm not going to go into the details behind this or so, but this basically we were, looking at this the data that we're getting from the ECUs in the car, and being able to determine from those particular types of data whether we can be able to predict or so that it will be a pre-ignition or not. Okay. Oops, sorry, go back here. So what my actually PhD intern did is that, he in 2018 at the International Conference on Intelligent Transportation Systems, he had already worked on a automotive diagnostics process. Okay, so he created a deep learning model where he took all the particular data from the ECUs that you see here, and it's recorded by this data, and then it's sent over offboard to his computer that he used, and he was able to then go ahead and label, for example, this based upon all this data, this was pre-ignition or not. So that was the training data set, and then from that data set, then we had the validation and the testing, and he created a deep learning model that uses convolutional neural network and long short-term memory, which I'll explain briefly in the next couple of slides. And so he created this deep diagnostics model already for that. Okay. So what exactly is the CNN and LSTM that he did there? So this convolutional neural network, and it's actually used in a lot of deep learning algorithms. Basically what it's doing here in a nutshell is taking the input from, let's say, for example, an image here, right? So let's say, in the autonomous driving car scenario or so, that it sees some particular vehicle or so, but doesn't know what that vehicle is, okay? So that's what we have here. And then through what's space has called feature learning and doing different particular hidden layers or so, and then classification, then out of this particular neural network or so, then it's able to determine that this particular image of a vehicle, whether it is a car or whether it's a truck or a van, maybe a pedestrian, or whatever this is, or even a bicycle. Okay, so that's what this convolutional neural network is doing. And then also too, there's something called long short-term memory. Basically, what it's trying to do here is that it's basically trying to add a memory component. So you have your input here, you have an input gate, and an output gate, and then if you want to, keep the memory or not, then you have this forget gate here. So this is the kind of the module that's being used to create this what we call long short-term memory. So this provides the memory aspect for the network. And so the thing is that we have long short-term memory, and we have a convolutional neural network, and we can combine different combinations of this, right, to be able to create a deep kind of learning network. From there, we can determine which one will give us the most accurate in terms of for no pre-ignition or pre-ignition. And so that's what actually Peter did in this work, and he found out that the combination of 4 convolutional neural networks and 2 long short-term memories gave the best possible architecture for pre-ignition detection. So that's what he discovered based upon the accuracy. Okay, so that was work that he did before he actually came to Chicago. So the work that we presented in the conference in Hawaii was about, okay, so we have this model here, okay? And then the next problem is that, well, that model was done on a computer, okay? So how do we take that model that's created, and how do we go ahead and we develop, manage it, and deploy it into the car, okay? And especially to thousands of cars. So think about, for example, if you have a particular machine learning model, in this case for pre-ignition, you want to deploy it to thousands of cars in your fleet. How do you go ahead and do that? So this particular problem wasn't really, addressed, right? We only just looked at, which was the most accurate model. But the thing is too, as well, is that this model that we created, even though it may be accurate, maybe it takes a long time, right? So maybe it takes a long time in the car, and we don't want that, right? We want to have low latency as well. So that's where we did this work. And in this work, we created this end-to-end framework using enterprise, cloud, and IoT edge technologies for training, testing, and deploying to thousands of vehicles. And so what we did is that from there that we evaluated the performance of the original data-driven automotive diagnostics network, that 6 CNNs and, the 4 CNNs and 2 LSTMs that I showed earlier. And we compared with other particular models, varying the number of CNNs and LSTMs to see, which one actually performs better in terms of like the time, and also in terms of memory requirements. Okay, so from there we created this, cloud IoT edge framework. So we already have, the model developments on a local machine. Right? We created already the ML model. So we have the training script. We have this pre-ignition data set, and then we created modules for the IoT. So if you're familiar with IoT Azure, so you need to create a particular module that can be able to be run independently on an IoT edge device. Okay, and so for this, actually, we use Microsoft Azure. So Azure provides an IoT edge framework of which you can create a module. So we create a module for the data source. Because the thing is that this particular data set that we had was not a streaming data set, right? We wanted to simulate, for example, that if we have all this, ECU data that's coming in, can we in real time to detect whether there's a pre-ignition or not? And so we created this PI data source that took the data set and just kind of like repeated, the flow of the data coming in to kind of simulate that process. And then we all had a pre-ignition scoring. So we have a scoring model that's based upon the data that would score whether it was a pre-ignition or not a pre-ignition. And then from here, then we can upload this to the machine learning workspace. And actually this machine learning workspace is where we actually did the training. So this is where you can take a lot of the resources before you would on the computer that maybe not be enough. And you can be able to try many different types of methods or so in the cloud in order to determine what particular model works. Okay, and then from there, based upon these IoT modules here, the PI data source and the scoring module, this gets upload it into what's called a container registry on a cloud. And then from here, they can be downloaded directly to this IoT edge device. So for our case here, because we didn't really have access to a vehicle that could have this IoT edge, we kind of like for our experiments, we simulated the process. So we actually ran this IoT edge device. We used a Raspberry Pi for this. So once we created this containers, then in the Azure, we have something called an IoT hub, and it can be, the modules can be sent over. And then Azure has an IoT edge runtime. Just like similar, when you have, your Java having a JVM. So you have this kind of a virtual, you have kind of machine here runtime, and then it's able to go ahead and run these models also directly on the device. Okay, so in terms of the pre-ignition data set, so in this work that we did, we had 1,600 plus test drives with special gasoline. So there was special gasoline that was used to actually create this type of pre-ignition. So in the beginning, from all the ECU data that we had about 1,681 features. Okay, so we had a high dimensional number of features in our data set. And then obviously, that's a lot of features. So there was some hypothesis testing that was done in order to then go ahead and identify this and drop this down to 484 statistically relevant features. And then for the labeling, then we had some experts that going to look at those features and was able to go ahead and indicate whether it was pre-ignition or not. So we had the labeling there. And then for our experiments, then we decided to use the top 50% of these relevant features. So that's 242 out of the 484, and also do the top 5. Because what we wanted to prove is that maybe you don't actually need to use all of these particular features. Only a subset would work. And then in terms of for the training data, from the data set, we had 70% training data, 15% validation, and 15% testing data. So in terms of for development and implementation, so we implemented, once we developed the modules from Azure IoT Edge, then they were then downloaded to a Raspberry Pi 3 Plus, and that was kind of to simulate the vehicle head unit. We trained the models. We used Python and the Visual Studio. We use Visual Studio. Actually, we use Visual Code. So Microsoft Visual Code for doing that. And then for the machine learning, we use the Microsoft Azure Machine Learning Service. And then we executed the predictive models using Python, using Docker and Azure IoT Edge. And then from there, then we visualize the results using Microsoft Power BI. So this particular table shows which models we decided to use for the experiments. So in the previous paper that Peter had or so, he created very many different types of models. And he calculated however number of network parameters was used for that model, and also the F1 score, which in machine learning terms basically can be equivalent to the accuracy. Okay, so you can see here why he chose 4 CNN and 2 LSTM as the best model, because it provided the highest F1 score compared to the rest. But you can see, the other ones don't really lag too much behind, right? And basically what we wanted to do here, right, is that, for the actual device, let's say in the car or the IoT Edge, if we ran this model there, maybe this particular model, because it's more complicated than this model here that is 0 CNN and 2 LSTM, even though the accuracy is a little bit less, but not too much, it may be that it may be dramatically much faster in this case here, where that means that if you were to implement it in the car, then maybe you don't need to actually have this complicated. Even though this gives you the most accurate, maybe we can trade a little bit of accuracy, but we have a better performance. And actually, the next slide shows that. So in this case here, we use top 50% of all those features from the ECUs. And then you can see here, we had different models. So we have the baseline here, which is using LDA logistic regression. So you can see here in terms of the accuracy, F1 score is the worst. It's like 69.2%, very, very bad, okay? But if you look at the mean predicted time, so we actually, ran, several runs of this and then calculated the mean of this. The time to actually run the particular model was only about 12.4 milliseconds. And if you combine this to all the rest of the other ones, then this is dramatically the fastest, right? But because it's the fastest, but in this case here, it's really, really bad accuracy, right? So you wouldn't select this, to put into your, into the, let's say the car or so. All right, so we look at the best accuracy here, right? 89.3. We found out that we got a mean predicted time of about 104, milliseconds, okay? And of course, if you compare to that, this is dramatically much more higher than this. Now, then you may say to yourself, then, well, okay, this is 89.3%, and we look at the mean predicted time here, why not maybe perhaps we could use this one here? Sorry, this one here, right? This 1 CNN and 0 LSTM, because this one here is the most, in terms of the predicted time, it is the fastest, the next fastest, right? After the baseline here. And we get a very good accuracy, right? 87.2. So yes, it's 2% different in here, but maybe in the grand scheme of things, it's not too much of a big difference. But we have a much, much faster time here. So then you might then say that for implementation purposes, that maybe that this kind of model here, even though this one that we had selected before was the best, might be much more better than this one. Okay, and then this shows you in terms of comparing the accuracy from our predicted model with the actual. So this was done in Power BI. So we had a streaming data set. So as it was going, it created this graph here. And you can see here for the green here is the prediction, and the black one here is the actual. And you can see for the most part, it pretty much matches pretty well. Okay, so that is for the predictive vehicle maintenance.
Just to,
so
Alvin, is it okay to interrupt? Just a question. So how
sure,
you
sure.
showed the prediction, the pre-ignition part. Maybe you can
Sure.
say a little bit, few more words on how and how much this helps to the BMW customer as well as BMW. How much, can you quantify some
right,
numbers?
right.
Yeah.
Well, I mean, I don't have any numbers in terms of quantification, but I think what I can say is that if we're able to actually predict or so when some pre-ignition is going to happen, then we could then notify the customer to say that, okay, maybe it's time that you should probably maybe take your vehicle to the dealership before it becomes an actual failure. So I don't really have any particular quantification based on that. This is based upon qualitative, but but hopefully you can kind of see that if we're able to detect in advance that something is about to have a particular fault or so, then we can actually address it much earlier rather than wait for it to actually become a catastrophic failure.
For this use case, is it really important to run it in real time or near real time? I can see that there might be some cases where you have to keep up, but this is a predictive maintenance use case.
Yeah. Sure. Yeah. So I mean, you may not have to. I guess it really depends on the use case itself. So yes, there might be some particular cases where yes, you don't need to do it in real time, right? So there might be cases where you can just once you have the model created and then you can just go ahead and implement the model. There might be some cases where you will need to create a more of a real time, and it depends in terms of what are the requirements and what type of latency that you need to get, right? So in terms of machine learning, some stuff might be run in the cloud, right? Some stuff might be run on the actual car itself, or you might have some IoT edge in between that's able to do something in between to be able to collect the data and to actually have the model run itself. So I think it really depends, right, in terms of what is the use case. So.
Allocating the different use cases between the car, between roadside unit edge, and cloud would be a very interesting problem for designing a system.
One follow-up.
Oh yeah, definitely, for sure.
One follow-up, when you replace some of the parts, you may need to retrain and create these models again. So how that works?
Sure. Yeah, so I mean, we didn't explore too much into that, but I think that, yeah, definitely, for sure. I mean, retraining is something definitely that, will need to be done. And I think what will happen is that, if you have a particular, model that's already in the car, so you have some new data or so that comes in because of things being replaced or so, then, yeah, you will need to have a way to be able to kind of, retrain again or so. Whether that retraining, actually happens in the car or not, because, the car may not have enough, resources or so to be able to run that. So then it might be, more beneficial or faster. So to just go ahead and, upload all of that stuff into the cloud. And then, once the new model is ready or so, then you could then deploy that model. So maybe, for example, what happens is that, maybe every nightly or so, right? When it gets, new data or so, while your car is in the garage or whatever, then it can do the update or so, online onto the cloud. And then when everything is done, you could then, over the air update can then send them the new model back to your car, so when you're in the morning or so, everything is updated.
And another
that hopefully answer part of it.
Another point is when you operate this vehicle in a different environment or different weather condition, these ECU data you are collecting can vary, right? Is that a concern when you collect this data for training?
That's a good question, actually. Because actually, the thing is that my particular experience or so is more on the I'm not I'm not an expert in terms of the the ECUs themselves, right? So what those actually those actual kind of data actually particular means per se. But I mean, what I would say is that I think probably yes, that if you have a different weather conditions or so, that I think that definitely that for some maybe ECUs or so, it might impact some of the data collected. But I'm not the expert in the mechanics part of the ECU, so I wouldn't be able to tell you. So I don't want to give you a false false answer. So
I see. Thank you.
I have a brief question about the platform. So I'm not sure if you mentioned this, but where you actually run the model in the data you showed, doing the inference, did that happen in Azure? Okay. That happened in Azure.
Yeah, it's in Azure. Yeah. So Azure has something called machine learning service, and we ran it there. And then once we had the model there, then we created it with using the we put into like a Docker container, so it was able to run on IoT Edge.
So is there any plan to have this run on the car? Because I mean, say the car's in a remote area for some time, and there is no 5G access or anything like this. You'd have to run it on the car.
I think there is. I mean, so I'm not in this space. This is something that we just did or so. So I'm not in this anymore now. But I would suspect that definitely that I think for sure that's definitely does have to happen. And I think also too as well. I mean, I think one of the reasons why this stuff doesn't really happen right now is that a lot of the cars themselves right now, in terms of the resources, it's not too much computing power there. So being able to run these machine learning models or so might be too complicated. So when the BMW kind of the head unit or so gets upgraded or so with much more resources and power per se, then you'll have the capability to be able to run this. And that's why also too as well, the cloud can also be a very good helpful too as well, right? So maybe certain cases you don't need to have it directly right away, right? So you can go ahead and take that data and upload everything. And what's good about the cloud is that you can have data from all different sources, right? To go ahead and upload it directly to the cloud, and the cloud can go ahead and process all that, with particular jobs, do machine learning and all these different types of data together heterogeneously, and then be able to create that, machine learning model, and then be able to, dump it back into the cars. And then of course, if the data doesn't change too much, then you just have the model running directly on the car, right? You don't need to connect to the cloud anymore, unless you need to do the retraining or so. Hopefully that answers your question.
Yeah, thank you.
So
okay, I think probably we will move on and keep the rest of the questions to the end. That's what probably Alvin wanted. Not too many questions in the middle.
Yeah. So anyway, Russell, this is the last use case that I have. So then we can go for questions afterwards. So.
Okay. All right.
So the last use case that I have here is using machine learning for personal preferences in the connected vehicle. Okay. So in this case here, so I mentioned, in the beginning regarding about, preconditioning, right? So this is also work that we had did and actually presented it in last year's BTC conference, 2020 fall. So it wasn't in Victoria, obviously, it was virtual. And so this was looking in terms of toward contextual and personalized interior experience. And basically what the background here is that, we wanted to, figure out, how we can do personalization in an automated fashion, right? So, customers, want to have, their vehicle personalized, right? The interior being personalized. So an example of personalization that you already have in the car, right, is like where, in the case that you go into the head unit, you go into the car, you can, for example, for seat heating, right? You can actually go into the driver or the passenger, and then you can automatically activate seat heating. For example, you can specify, how many degrees Fahrenheit or degrees Celsius that it has to be below. And then you can set, for example, what is the heat level that you want. Okay. But obviously, this is personalized, sure, but this is something that has to be explicitly done, right? So that's why I say here, personalization exists in the vehicle, but it's based on explicit driver preferences, right? The driver has to explicitly specify what is that personalization. Now in BMW Connected, we did have something where we said, for example, you could schedule ventilation. But again, this also is explicit, right? You have to, manually select it and be able to send it to the car, okay? Let's say, for example, in the case of for preconditioning, let's say, would it be cool or so that because it knows from your previous behavior, let's say, in Chicago or so, that when the temperature is, below maybe, I don't know, maybe 30 Fahrenheit or so, it knows that in your previous behavior, you will, have the heating, or you will have a certain part of your seat heating that happens because that's your, habit, right? So the whole idea here is trying to learn those particular habits, and then from there, from the machine learning, and then from there, then go ahead and send notification to the customer to say, you have your next trip coming up, right? So I talked about earlier, right, in journey management, regarding about, when is your next predicted trip. So you see here how we're combining these things together, right? Journey management and personalization. So based upon your next predicted trip, because it knows you're about to leave for the next one, and it knows what's the temperature right now, and what is your behavior, then it can go ahead and tell you and say, recommend to you and say that, hey, do you want to have your car heated? And then based on the user that said, okay, yeah, it's good. You give me a notification to say that I want to have the car heated beforehand. Then when the person goes into the car, then everything's all heated up or so, right? So it's extremely very helpful, especially in winter times here in Chicago and other cities and states too as well. Okay, so that's the kind of the context behind this. So in terms of previous work, I mean, there's been other work on this. So for example, there's a patent here from GM that talks about automatically waking up a vehicle and performing preconditioning before the requested departure time. There's also another one that looks at remotely starting the engine of the vehicle depending on the temperature. But this is more of like on the actual the vehicle side itself, right? This is actually looking at the actual the engine itself or so. There's also work in terms of like using machine learning to recommend personalized audio content for personalization, for infotainment, obviously for ADAS too as well. And actually we presented a paper actually a year before in 2018, where we actually created a machine learning model for automatically learning seat heating preferences. So in this work, what we are trying to do here is that, how can we create a system for a personalized smart interior that can provide a proactive and a comfortable user experience? So we use the example of predictive preconditioning. So in the case of predictive preconditioning, what we want to do is that can we recommend and notify drivers when to precondition their vehicles, depending on the vehicle's parking environment, the user behavior, the departure time, and weather. So one thing to also consider too as well is that you need to consider the vehicle parking, right? So for example, if the vehicle is inside a heated garage, then maybe you don't need to have that vehicle to be heated up because it's already heated in a heated garage, right? So our solution and contributions here is that we created a machine learning framework for predictive preconditioning. And then from here, we actually, once we created that machine learning algorithm, then we actually deployed it into BMW Connected. This was about 2 years ago or so. And then we recommend notify drivers that they should do some preconditioning, considering the weather, the departure time, the user behavior, and the parking. And then we evaluated the performance and the effectiveness of the algorithm. So we actually did some data analytics on this, and we actually had users, provide feedback. For example, in the case of like if they actually did, accept the notification, or if they, ignored it. Okay, so this is kind of the workflow as to how this works, right? So think about, you have your vehicle, right, and the vehicle is about your parking, and then you start, okay, and then what happens here, okay, is that you need to know whether it's a predicted departure, right? So are you actually departing for a next trip? And so if you are departing for the next trip, before you start your trip, then what we do is that we get the current weather to see what it is. And then that weather information plus the predicted departure gets put into a smart preconditioning model. And then from there, we determine through machine learning whether there's a need to whether you should be preconditioning or not. So then we go to the next part that says if there is a need for preconditioning, then we go ahead and send notification to the customer, and then the customer accepts it, then we go ahead and precondition the vehicle. So actually the preconditioning the vehicle is just like a command or so that comes from the app. It sends over to the vehicle, and then the vehicle then will be preconditioned. So preconditioning can be, for example, be heating the car, or maybe it could be cooling the car, or even ventilation, the fan. Okay, and so basically after we had this predictive preconditioning algorithm, then we displayed it to the user. Okay, so in here we can show you here that there is a notification that says that, okay, you should maybe have predictive preconditioning. In this case here with my X1 that I was testing to go to the United Center. And then from here, then the notification goes ahead and says, the user can decide, whether they want to start preconditioning or not. Okay, so the thing is that, we want to still give users the control, right? So we don't want to automatically, cause the predictive preconditioning, and we can have the user decide whether to actually do it or not. But the whole idea is that to provide them the option, ahead of time, because maybe the thing is that they didn't think about it, right? So this is the whole idea, is to provide this kind of, convenience and personalization. All right, so how does this work in terms of the predictive preconditioning model? So I won't go into excruciating details. But basically what happens here is that we first of all need to collect, all the history driving data about the user. So we collect the location data, we collect the exterior temperature, what's the interior temperature, and what's the weather temperature. Okay, and then from here we create this global preconditioning model. And so for this global preconditioning model, we do feature extraction. So we look at the wait time between the first car record and the first record of the temperature. We look at the difference between interior temperature and exterior temperature. And we set particular criteria, right? So we have a particular threshold that defines what is considered cold, temperature. And then we see what the actual outdoor temperature right now is. And if it is less than a particular threshold for cold, then we can say that at the beginning, when you're actually driving, your X records of data that we collect means that you were, that means that you were, let's say, outside or so, okay? And then we also do the same thing for interior temperature as well. And then we also have a function to determine the outdoor parking probability, whether you were outdoor or whether you're not. And then basically from all the data from all the users, then we create this global comfortable temperature model. So we kind of see what particular type of temperature that people found is comfortable, that they did not actually do the heating or the cooling. Because we also know whether they actually did heating or cooling, right? So we also have the data too as well, so the labeling data. And then from there, we get this global preconditioning model that combines all these together and then uses supervised learning to learn a relationship between preconditioning, exterior temperature, and wait time. Okay, And so then from there, once we have this global preconditioning model, then we can start to use that to do the personalization. So once we have the personal user's driving data, then we can adapt the global preconditioning model. And then we can create a personalized preconditioning model based on this. So if you're a new user, right, you don't have any particular data, then we first of all use the global preconditioning model to predict first. And then as you are driving, then we get the personalization, and then we can go ahead and adapt that model. So you can see that here. Okay, and basically, won't go into like, excruciating details, but if you're interested, we use a bilogistic regression, which looks like the following. And then we define what are the personalized parameters for this particular model, and then we optimize it. Okay, and then based upon that, once we get the actual decision, then we can get the user's feedback to see whether that person actually, from that notification, whether they actually, pressed it to say confirm that they want the preconditioning to start it or to not. Okay, so the preconditioning decision is made based on the model output. And the thing what we also have here, I mean, we didn't implement this, but what we could do is that, if there's a high confidence level that we know for sure that the user will want to have preconditioning, and it happens all the time because, the user always keeps on confirming, then we can learn to the point that say that we can automatically precondition. So we don't actually have to give the notification to the user and it would automatically do the preconditioning, only if there was a high confidence level. And obviously, if there's a very low confidence level, then you would do nothing. Okay, and then based upon the feedback, then we use that to update the model parameters and adapt the personalized preconditioning model. And I'm almost finished here. So in terms of algorithm evaluation, you can see here that this is the data set that we kind of use to test this out. So we have the exterior temperature in degrees Celsius in the horizontal with the interior temperature. And then we plotted these particular points to see what's the relationship. And then from here, we were able to determine based upon exterior temperature, whether the user would want to have preconditioning or not. And then from here, from our model, the biologistic regression, we had 240 trips that we looked at, and we found we had an accuracy of about 91%, precision of 76%, and a recall 89%. So it seemed to work pretty good. And then in terms of for the data analytics, so this particular graph, kind of shows in terms of the notifications, the precondition notifications that were sent. So in orange, you can see is the number of heating precondition notifications. So you can see there's much more than in the case for the cooling. And this was actually done using the data from Europe. So in Europe, it seems to be that, even for when it is like, maybe 4 Celsius, in this case, maybe 6 Celsius here, that it was the most number of, preconditioning for heating. And so maybe this might be a little bit different in the case for the US market, but we use the EU for this. Okay, so I'm on to my last slide here. Basically in summary, what I discussed about, so I talked about, how machine learning can be used to learn driver behavior patterns for journey management. And then I talked about how we can use machine learning to predict faults of components before they become failures for predictive maintenance. And then finally, I talked about how machine learning can be used to learn users' personal preferences in the case for the predictive preconditioning. And basically, what I kind of advocate here is that, the machine learning can be used, so we call it, BMW slogan, right? It's the ultimate driving machine. So then, I think the machine learning can be used to make the ultimate smart driving machine. So I added the word smart here. Okay, so basically, yeah, I'm finished here. So here are my credentials, my email, and my website if you want to know more about the papers that I had presented tonight. And I'm ready for any questions. So thank you for your time.
Thank you, Alvin. So time for questions. Please unmute yourself and ask question.
Hey, Alvin, this is Randy. Can you hear me?
Hi, Randy.
Hey,
yes.
So I'm curious, does this mean that PII, personally identifying information, is then going to be retained with the vehicle in all instances with this?
Right, that's a very good question. So actually, what happens currently right now is that, if you have an associated vehicle and let's say you trade in your vehicle, then all that stuff is going to be removed. So if the vehicle is switched to another, let's lease a vehicle, right? And then the thing is that when you return the vehicle or so, then all that stuff you had from the data or so, will be removed. So then the next customer that gets the vehicle will not be able to see, because because that is true. Because what happens, for example, because if you have this vehicle and have all this data, and another customer then takes that vehicle and then gets recommendation of something because of that previous customer, then of course that's not good, right? So yeah.
Correct. Yeah, but because there's different privacy requirements, you would then have to, maintain, because even if it's out and about, maybe there's a need for encryption, right? So have you looked at homomorphic encryption as a possible solution? Right.
So from my particular knowledge, from what I worked in the project on this, we didn't, to my knowledge, I'm not familiar with particular that. But it's in the case of for PII, what I will say is that customers do have with the BMW connected app, and I'm pretty sure as well with the My BMW 2 as well, is that they do have the option to be able to opt out, or to be able to say that I want you to delete all my data or so, if they don't want to use it or so. So they do have they have the power to be able to decide whether they want us to collect the data or not. Actually, in the case of Ford, actually I neglected to mention is that you talk about privacy or so. One thing also as well is that even though we recommend to the customers of BMW Connected that you should have your location turned on all the time, so we're able to collect and get the machine learning. It's not required, right? So the thing is that in the settings or so, the users can decide if they want location to be collected all the time, just like you have with your other apps too as well, right? On your iPhone or on your Android phone, similar thing as well too. So the thing is that we tell users that we would prefer you to have location on or so we can be able to collect it and give you more accurate results, but we don't force it upon the user. So of course the user can decide I don't want you to collect this data or so, and then obviously we won't have accurate results per se, but if that's what the user wants, then we honor what the user wants, right?
Kind of related.
I hope that kind of answers some.
Yeah. Yes.
Yeah,
one kind of side item is there's a lot of sensor technology, potential RF, and a lot of people's pets now have tags in them. So are you looking at potentially using sensor technology to monitor for pets in an automobile, and potentially use that as an alerting mechanism in the event that there is a pet in a car and it's getting warm?
Yeah, I think for sure, definitely that is something to consider. Yeah, definitely, I think so. I think, and that's where I think all these IoT stuff or stuff that we have, our sensors, our watches that we have that detect this and that or whatever. Yeah, I see that definitely that is something that could be done.
Yeah, because I think the car actually has potentially already has a mechanism to ping the tag. So just a thought.
Right. I'm sure a lot of these things are being thought about by the next generation of vehicles that we have. So yeah, thank you for the question.
Any other question? Maybe I'll ask a question. So in your first case, the trip management and all, so the most of the intelligence and the processing in the phone, right? Not in the car. Is that right?
No, so actually, so what happened is that the data was collected from the phone and from the car. That was then uploaded into the Azure, into the cloud. And then all the machine learning stuff is actually done in the cloud.
Cloud, yeah, okay.
So then once you have the machine learning stuff in the cloud, then when the user, let's say, refreshes the app, then they will see, their destinations or whatever new information.
And what kind of connectivity that you envisioned for this study for the car? Is that like a 5G kind of thing, so cellular?
Yeah, so I mean, currently, I mean, we, for the BMW Connected, right? Everything was just based upon, collecting the data from the car into the phone, and then the app would collect that data, and then it would then send it through your phone's, network connection to the cloud. But now the thing is that, with the newer cars that we have, the iDrive 7.0, you don't have to have your phone paired to the car anymore, right? So you can just basically just, log into the car, and then the car's data would automatically be sent to the cloud. So there's no need for pairing the phone. So one of the things that, was before with BMW Connected was that, you had to pair your phone over Bluetooth in order for it to work.
So what kind of connectivity is in there in the car?
So the car is just using, regular cellular technology. So it's already like, I mean, if you purchase a BMW car, you want to have the connected option, or so there's like a SIM card already inside.
I see.
The technology you're describing only requires radio access network, mobile network for infrastructure. Are you doing work assuming more elaborate infrastructure if it gets deployed widely in any particular locale? Like imagine.
I mean, I'm not working on this, anymore, but right. But I would probably imagine so. I mean, I'm not working on this pretty much anymore because I moved to a different department, but I do suspect that probably, yeah, there will be something like that.
Do you have any forecast of how soon that will happen?
To add to that, yeah. No, sorry.
Do you want to ask the question? I think, he's in Chicago. Somehow, there is a big delay in there. I think the question, yeah.
Okay, there might be a network delay.
Yes, I have a question.
Yeah, sure, go ahead.
Yes, on slide 32, you showed the predicted pre-ignition based on DADN versus actual. 32,
oh, right, okay.
32, and
let me see if I can get yeah.
Yes, it doesn't seem to be that much accurate.
Yeah, 1 second. It's a bit slow on my end here. Trying to go back to the slide. I had a lot of the animation. 32 what it was?
32, yes.
32? Okay, almost there. This one here, right?
Yes, exactly. And I'm just referring
this
to
graph?
this spikes, green spikes between the like pulse-shaped, maybe.
So you mean here, right? You mean here?
Maybe the golden model that you have. Yes, that's and
that
but here you have here, and you have also the two next one to the right side, the second next one. Yes, this one. And then altogether, if you count the number of the mispredictions, like for the whole day, I think that's a lot. And but
yeah, so I mean, this is just a snapshot. This is a snapshot of So I just took kind of a snapshot of the because it was like streaming, so it was like going, and I just kind of took a snapshot, of this or so. So. Yeah, I mean, if you look at it in detail, but I think if you combine it, with if you do this on a longer time frame or so, then I think you would probably get to a point or so where it would be somewhat kind of accurate. So.
And is it related to the F1 score that you have on slide 31? And then with what is the measure of measure of your accuracy here?
Also, this is basically based upon, so in the case of for the prediction, right? So that is based upon, so the things that we get an output result, and then an output result is a score. So basically it's just a score, just a numerical score. And then the numerical score is basically determining whether that is 0 being no pre-ignition and 1 being pre-ignition. So that particular model, right, what it outputs is a particular scoring. That's what I mentioned about before about that PI scoring, right? So that PI scoring is actually giving you a particular value. And then that particular value, depending on where the range it lies, then that refers to whether it is a whether that is a pre-ignition or whether it's not pre-ignition.
Yes, but when when you want to use the green curve, you just map it to 0 to 1 to actually make a decision. Yes. Then for the first case,
right, exactly.
probably
Yeah.
when you have these two spikes, they will be mapped to maybe probably 1. Anyways, you guys need to add some thresholding here, and for the other one, it's probably about 0.5. I'm referring to the one after 3 p.m. Little, and
Yeah. Okay. Yeah.
that's yes. Then okay, and sure.
Yeah. So obviously, yeah, you are right. There are going to be some miss ones here that you can see, but yeah. But I mean, so obviously, this is just just a sample or so. I mean, you got to take this with a grain of salt, right? It's not, you have to do considerably much more more in-depth, detailed detailed analysis or so, right? So the data that we had was just based upon just by putting some test gasoline in there and just getting all these particular results or so, right? So whether this actually translates into the actual vehicle itself, there probably will be some more things that need to be added, but I think what I'm trying to say here is that that we do have a possibility that we can create a particular framework, and if we wanted to then take this to the actual car, and once we had that data, that we could actually go ahead and do so.
Okay. Thanks.
Yeah, sure.
Any other questions? One more question from me. So, the 5G brings a lot of low latency capabilities here. So in your research or
Sure.
BMW, how much, they are taking advantage of it, maybe you can comment on those.
So, I mean, not too much in terms of into this 5G space or so, but I know for sure that obviously, for the next generation of vehicles, there will be 5G. And I know that, BMW is part of this, what's called, I think it's called 5GAA, something like that. It's like a automotive alliance or so, right? And they basically, what they're working together with other companies and or so is they're trying to create this kind of like using this, V2X, right? Cellular V2X, right? Technology with 5G to be able to do, V2V communications with the cars. So being able to look at 5G and be able to see, okay, if another car is coming and so communicating over 5G, able to automatically, in the case of for autonomous driving, right?
Okay. Any other questions? Anyone? Probably one more last question from me. So in the new division in BMW in Bay Area, so what are you going to do? What area
so
you're going to
basically
work on?
our team is doing right. So I'm actually, it's a little bit different. So I'm working on using like AI for modeling for like so what we're trying to do is we're trying to do some automated machine learning. Automated machine learning. So for a lot of different, BMW business units, they have particular problems, but they don't have, actual machine learning experts per se, and they want to apply machine learning. So, rather than having to, find someone that knows it, or in terms of like having to write the code for it or whatever, how can we use, automated machine learning platforms, to be able to, once they input the data, they can, go ahead and not having to know, maybe the actual details of the different algorithms, and not having to have to worry about in terms of selecting which algorithm to use, right? Because one of the challenges, right, in machine learning is that, what particular algorithm, unless you know exactly what your data is, right? Whether it is a classification problem, right? Whether it's a regression problem, whether it's a prediction problem, right? For people who are not in this data science area or not in machine learning, they probably will not know what that is. And the whole idea of automated machine learning is basically, bring machine learning to the masses, so they don't have to know what to do. So they just import the data, and then the automated machine learning will go ahead and try different algorithms, right, that it knows, because it can go ahead and study, what is the relationships in the data that's in there, and then determine which particular models that it will try, and then it will give you the output, and then the explainability of the models, and then for the business analyst will be able to look at the results and say, oh yeah, that's what, the prediction was correct, or the accuracy was good, or not. So that's one of the projects that that I'm working on. Also as well, I'm working on some exploration with neuromorphic computing. So yeah, so doing some stuff to see, how neuromorphic computing. So basically, deep learning, has its challenges in terms of that, you start, once you get so many, layers or so, it gets very complicated. And one of the problems is that, and if people who are working in deep learning is that, we try to run on a GPU, right? Like an NVIDIA GPU or so, it gets very hot, right? So it consumes a lot of, power, a lot of energy. But neuromorphic computing actually has an architecture where actually you can actually run a deep learning algorithm, let's say faster, but also have much low power. And we're really interested in neuromorphic computing because if we were able to use that in our cars, right, then we can lower power consumption, and we can be able to run lots of, applications or so. Neuromorphic computing actually uses a different kind of architecture than neural networks. It's using something that's called SNN, which is called a spiking neural network. So neuromorphic computing is kind of like mimicking, the cortex, how your actually brain really works in terms of the signaling firing of the neurons. So that's more towards, how the brain works. Not that neural networks doesn't do that, but the neuromorphic is more geared towards how the brain networks. So that's another particular type of project I'm looking at to see how some of that can be done with some BMW use cases. So.
Okay, great. Any other questions?
Sorry, just one more question. On slide 16, you have a plot showing fuel consumption versus travel speed, and is it realistic?
Oh, okay, yeah, right.
You have
yeah, 1 second. Yeah, I know what you're talking about, the Gaussian distribution, right?
yes,
This one
that's
here, right? You're talking about.
yes,
Yeah,
then
so I mean,
does it
this was right. Sorry, you were saying?
does it mean that if you increase your speed to 100 or 120, your fuel efficiency will be better?
So this was so actually in terms of actual implementation or so in the car. So actually this particular work actually was not actually done by me. It was another researcher that actually did this or so. But I believe, if I remember, that I think that this was what we had calculated. But I think when we actually implemented it, in the car per se, that we kind of like did some modification. So I don't think it's exactly, but it's something similar to this. Yeah. So actually, the actual production version of it was not exactly per se this, but nonetheless, right? What I'm trying to say is that how we can be able to use machine learning, use algorithms to be able to try to map a particular function to the data, right? So whether it was exactly this or not, it's just trying to show that we were able to actually improve the the fuel consumption, by doing, this type of algorithm.
Okay, thanks.
All right.
Yeah.
Okay. Thank you, Alvin. It is very late in the evening for you in Chicago, I guess. Thank you so much for taking your time and giving very interesting and engaging talk. Thank you. Thank you very much.
Yeah, thank you.
Thank you, Raf, and thank you, everybody. Thank you very much.
Yeah. And for the rest of you, thank you for staying up
Take care.
with us late, and have a very good evening.
Thank you.